Today we are going to, I'm not going to be the facilitator of the workshop. Mr. Koza Stanford will facilitate the workshop. He will share with us the quantitative approach to research, particularly in engineering fields, in engineering sites. You already are aware that we have opened the channel for presentations, and that the majority of you who are interested, you are welcome to also share your work with us. This is the reason why we've got Stanford. On Thursday, we will have Kidiboni, and she will also have her own presentation. And through that, we will engage. This actually confirms that all of us own this program, we own these workshops, and we will continue to give each other that approach.
Good evening, colleagues. My name is Stanford Kosa. I'm a student doing BSc Honours in Computing. I've completed my national diploma in DUT in 2010. Then I continued with my studies, did PGCE, specializing in physical mathematics and technology for senior in FET. But I never had an opportunity to be a teacher. I'd love to be one sometimes to come. Then I also went ahead and did my BTech in computer systems. Now I decided to shift my focus to computing, focusing mainly in AI, but I'm still in engineering. So what I like about engineering is that, as Peter says, what gets measured gets managed. So if you have anything that you want to manage, you need to get data for it. So today we'll be looking at quantitative research in engineering's perspective. And then colleagues, as we proceed, please do ask questions, do put comments. If something is not clear, it's not a one-man show. Let's all participate. And I most certain that after this session, we'll get something from it, as we usually get something from different sessions. So with quantitative research in engineering, it's often seen as a tool which we gather information or we gather data to ensure that we analyze that data, and then after analyzing it, we are able to use it in a way that it will help us to make better decisions in mining. So my introduction, quantitative research provides measurable numerical insights into mining operations. So mostly of during this presentation, we'll be mostly talking about mining and instrumentations, because I am an instrument technician currently, moved from different environments. So it's very close to heart, because apart from it being an academic thing, for us, it's a reality that we live with at our work areas. So it helps us as engineers to ensure that the decisions that we make, they are based on evidence, which is the data that we collect, to ensure that we improve efficiency, safety, and productivity. And the reason we want to do that, it's simply because we need to ensure that the operation runs smoothly and we are able to make, obviously, production, which is money to the company, money to pay the people, and we need to do it safely, so in a very efficient way, using as less energy, as less resources as possible. So the background of the study is that mining operations are increasingly data-driven. So everything that we do in mining, data is the most important thing that we need. So instrumentation on its own, it plays a central role in monitoring equipment health, environmental condition, and also coming up with safety metrics. So with quantitative research, it provides the foundation for transforming raw sensor data into actionable insights. And this, it enables us to ensure that we optimize performance, we reduce downtime, and we also enhance safety, because in mining, safety, it's the biggest priority before production in anything else. So, but despite the availability of advanced tools like IoT's Internet of Things sensors and SCADA systems, many operations still rely on reactive strategies due to gaps in data integration and predictive analysis. So this, by this study, it's to show what is it that we are planning to improve. So the problem statement that we mainly focus on is that we need to ensure that unplanned equipment failures, particularly in critical systems like crushers, and which results in costly downtimes, safety risks, and operational inefficiencies. So traditionally, maintenance approaches are reactive, which lack foresight to prevent breakdowns. Because in mining, most of the things, it's all about machines and all that. So this raised a need to demonstrate how structured quantitative analysis can shift mining operations toward proactive and data-informed decision-making. So with us, data, it's everything. And data comes from, it's research. So research does not only end in class. Research, we use it as a daily basis tool in engineering, because with how things are evolving, it's going through that manner that we need information. Information enables us to ensure that we make decisions. So the purpose statement of this study is to illustrate how qualitative research method, including descriptive statistics, regression modeling, time series forecasting, and anomaly detection, and how it can be applied to mining instrumentation data to predict mechanical failures and improve operational reliability. Because in all that we do, we need to ensure that the machine reliability is up to par. The mean time between failures, it's on point. So as I've said, for us, it's not just academic work, but it's the work that we do on a daily basis, and it's the work that we ensure that we keep people safe. Because mining on its own is classified as one of dangerous environments. So hence we need data. Data help us to make decisions. So the research objectives for this study is to define a baseline operating threshold using descriptive statistics, and to model relationships between sensors readings and equipment wear, and also to forecast failure trends using time series analysis. So with this, what we need, or what we want to achieve, is to ensure that we collect as much data as possible from our remote sensors, so that we minimize human involvement in having to collect data, so that we can then make our analysis and our decisions based on that. So we also need to detect anomalies that signal imminent breakdowns, and to evaluate the impact of predictive maintenance on downtime and cost savings, and also to explore safety applications of quantitative data in mining environments. So that is our main objectives. So the hypothesis in this research. So we'll be looking at two hypotheses. Another hypothesis, this assumes that the fluctuations in vibration readings does not have any effect in the downtime, or does not correlate with actual mechanical breakdowns. So with this one, this is our null hypothesis. So which now we want to, the reason we collect this data is to ensure that with our alternative hypothesis, we need to check which one of these two is actually valid for us to be able to ensure that we make well knowledgeable decisions from the data that we collect. So our alternative hypothesis propose a direct measurable ratio between rising vibration levels and the likelihood of equipment failure, particularly in rotating or impact-intensive machineries like crushers. It suggests that vibration data can serve as predictive indicator, allowing engineers to intervene before a breakdown occurs. So with that said, colleagues, when a crusher stops, basically most of the mining outgoings or products, they stop, because from having to dig from the ground and sending to the concentrators, the crusher for us, it's the biggest link between the two, because if we cannot crush, it means we cannot process. So if we cannot process, it means whatever that we are mining, we are not making any gain from it. So that's what we look at. So for it to assist us with the hypothesis, we need to evaluate this following. So we use regression analysis to qualify the relationship between the vibration levels and failure events. And by so doing, we will apply the p-values and confidence intervals to determine the statistical significance. And then we conduct time series analysis to assess predictive patterns over time. And we use also anomal detection to identify thresholds that reliability precedes mechanical issues. So it's already with what we need to focus on. It's a big deal for us, because we need to ensure that with all that we want to do, we must make sure that we do get data that is reliable, data that we'll be able to use to ensure that we get to what we need. So, with our null hypothesis and our reactive, what happens is, after receiving the data from our remote sensors, and we analyze it, and then we make a certain progression. When such time correlates with our preventative maintenance, to realize that indeed, let's say maybe there's a bearing, and then with the data that we've collected, we then estimated that in 2 weeks' time, this bearing will be an almost failure. So then, with the data that we collected and the findings that we go to, because data on its own, no matter how much data you collect, you need to somehow do qualitative control over the quantitative data that you gather. So by so doing, we then are able to grow in the future to say that we are able to rely or put trust that what our data give to us indeed will be almost to a reality of what's happening. So with quantitative research in mining, we focus on 3 things: systematic, numerical, and objective, which forms part of the quantitative research definition. So with systematic, we follow a structured method. Obviously, we need numerical values, to which comes from the data that we measure from our instruments. And then the objective is to minimize the bias through replicable analysis. So quantitative research method are applied to ensure that equipment performance monitoring is done, all grade analysis is done, safety monitoring is done, environmental compliance is done, and to ensure that the process is optimized, because it does not help that one of these 5 aspects lacks, because they need to go hand in hand to ensure that all that we do it in a manner that does not harm the environment. We do not cause any injury to anyone, and the clients that we give this ore to, we are indeed giving them the grade that they want. So I'm sure now colleagues are now wondering, is it still a academic work or it's now a work thing. As I've said, with mining, quantitative research is not just another research, but it's something that we live with on a daily basis. It's something that we rely on a daily basis, because that is what we live with, and that is what we do, and that is what we rely on to ensure that all that we do, we do it safely. So with data, there's two terms that in mining, specifically in instrumentation, we focus on: accuracy and precision. These are the terms that used to describe the quality of measurements or predictions. So now imagine this being our target board, and we need to throw darts aiming at the center. So from the left to the right, on the first one, there is high accuracy because all the 5 darts that were thrown, they are almost at the center, but the precision is low because they are scattered all over. On the second one, there's low accuracy because now if you check, they are at almost at the outer layer of our target, while we need to be at the center. But then now there's a high precision because all our darts, they've hit on one point. So now if you are not carefully, you may then take this high precise data thinking that it's accurate. So now when we get that, what we then do is we go look at what we call the calibration certificate. Now you are using quantity data, and then you bring up the quality, which is ensuring that the data that we are receiving is indeed a quality data, or it's indeed data that present or demonstrate the actual happening. So on our second one, we see that, okay, the data is highly precise. It's almost true because it's more or less in one point. But then if we check the accuracy, in this case, you may find that maybe the instrument that you are using is out of calibration, or it have shifted, because some instruments, the position where they were initially installed, it does have an impact if they happen to shift. So now on the third one, we have high accuracy and high precision. This is what we want, to ensure that the data that we have is precise and is accurate. So this is each and every person in engineering, and I also believe in health, in education, everywhere. This is what we want: data that is accurate and precise, to ensure that whatever conclusions that we make from this data, we are making it in a way that it represents the real world. So on the fourth one on the right, there we can see the accuracy is very low and the precision is very low. So colleagues, with this slide here, in your different disciplines, I believe somewhere, somehow, we do, all of us, or majority of us, use these two terms, even though maybe we may not be aware what is it that we were doing, or maybe we apply differently from engineering. I would like us to share your views or your encounter with precise and accurate accurate data in your fields. Unfortunately, I'm not able to see hands, so I'll allow anyone just to unmute and give me a bit of what they can relate regarding accurate and precise data in their disciplines. So you know, in instrumentation, we want our data to be both precise and accurate, so that we are able to make very well informed decisions with the data that we have, because we do not want a situation whereby we then say something while the data does not represent the actual thing. So imagine if maybe now we have a temperature sensor that now we go and collect data from it, and then after collecting data from it, and then we say now we want to automate the system to say that, okay, we need to ensure that the room temperature is between maybe 21 and 25, for example. And then now, by so doing, you find out now our temperature sensor, it reads maybe 10 degrees lesser than the reality. And then now it means in actual sense, what we are trying to automate, instead of getting our 21 to 25, when then running on 31 and 35. At the end of the day, now we are in a position whereby we are not getting what we were supposed to be getting. You know, with accuracy, this refers to how close the darts that were thrown are to the center of the target. You know, this I have explained much in the slide that I was showing you with the 4 boards. So let me jump to what is it that in instrumentation or in mining we can relate our data in connection with accuracy and precision. So in instrumentation, accuracy is the degree of which a measuring instrument result is close to the true or accepted value, while precision is the degree on which multiple measurements are of the same quantity, are close to each other, indicating repeatability, but then not giving us the true value. So as an instrument, it can be precise but inaccurate, or you find that it's accurate but not precise. So what we need is high quality instruments are both accurate and precise, yielding repeatable measurements that are close to our actual value. And then we get this by ensuring that with the manufacturers, they have something that we call a recommended calibration period. Most of the instruments that we use, they will say each and every year you must calibrate and have a calibration certificate. Because if anything happens, let's say we injure someone or we kill someone, even though that's not what we want to do, and then the DMR comes and say, okay, what happened? And then we say it was an instrument failure. First question, when last was it calibrated? Before they get to the data that was received, they want to know when last was it calibrated. So now you see, before they jump into the quantity of the data, they want to be sure of the quality of the data that we have accumulated. So that is why we make the point that we need data that is precise and accurate, you know, and then to achieve that, we do what we call calibration at each and every given time interval recommended by the OEM. So I'm going to give you an example of it's a truck. We did a study in January to make sure that the calibrations that we've done on our dump trucks, they are indeed a real thing or close to what we want. So we had a couple of results that showed the 3 scenarios: accurate but not precise, precise but not accurate, and also accurate and being precise. So this dump truck, actually, it must be loaded 40 tons. And then now, as we load it, when then the scoreboard says 40 tons, or it gives something close to 40 tons. So in the first scenario, so with the average is correct, but then the readings vary. So the first load, the truck loaded 38.2, the second load 41.5, then the third load 39.8, the fourth one 42.1, and the fifth one 38.4. So with what we see here, we then take this data, and then when we get our average says that our weighing system is correct. It is working the way we want it to work, because of we have taken the average. So now it gives us a data that is accurate but not precise, looking at each and every individual load. So now we look at the second scenario, being precise but not accurate. So now here a truck was loaded 42.9, 43.1, 43.0, 43.5, and 42.7. But on the scoreboard, it was reading about 40. But when we take it to the weigh bridge, this is what we found. So now when we analyze, we realize that, okay, these values are very stable. And you may mistake it as the right data that you need. But then now when you look at an actual reality, is that the values are not corresponding with what the truck have registered on the scoreboard. Then on the third scenario, we have 5 loads, 39.9, 40.1, 40.0, 40.2, and 39.8. And then now when we check this and we average it, it gives us about 40 on average. And also when we look at it, we do what we call round off to the nearest 10. We realize that when we do a round off there, we do get our 40, 40, 40, 40 as a round off. And then also when we do our average, it gives us the 40 that we need. So then we go thumbs up. This is what we do. So then what we then do is we go check the calibration file that we have used. Go check those other tracks that are not giving us the values or the data that we need to ensure that we balance and modify our calibrations in a way that it will give us data that is accurate and precise. So with that said, colleagues, it does not mean that having all these fancy sensors and all that we are sailing nicely. We do have challenges. We do have challenges that really affect our data reliability, because unfortunately we live in an environment that we cannot close up whatever that's happening outside. And you know, with mining environments, they are very harsh. And the thing is, with those harsh environments, they have real consequences on our measurement accuracy. For example, dust can coat a sensor and scatter signals, and then you find out mostly in optical or laser-based instruments, dust is a problem. You know, so that is the first challenge that we have, is data interference. You know, particularly building up on sensors which distort readings. And then again, another one is temperature. You know, unfortunately in Limpopo, I mean Mokopane, it really gets cold. And places like Uppington, it really get hot. And then you find that we are using the same sensors, but then with different weather conditions. So again, extreme weathers, they whether high or cold, they affect our sensor sensibility and our calibrations. So this brings that, you know, some instruments, they will recommend that maybe it's a seasonal calibration to ensure that what we have on our calibration file cater for the difference in temperature, because temperature does have it does have impact on what we measure. And you know, with that said, this is the reason why calibrations are needed. And in most cases, you find that maybe we also install 2 sensors to make sure that we have data redundancy, to check that, you know, how accurate or precise these 2 sensors with in terms of the data that they are giving us. You know, because now by so doing, we need to ensure that our data, we use it in a way that we will make a decision that is well informed, based on the accuracy and the reliability of our data. Because if we don't take that into account, you find out we end up having data that is unreliable. And once we do that, we then make decisions that are wrongly misled by something that we feel or we thought it's there to help us, but yet we're setting ourselves for failure. So with this, what my take or my give to colleagues is that no matter how much quality data you may get, I mean quantity, no matter how much quantity you may get, and by a mere look, you may feel that it's quality because of the closeness to each other. We also need to ensure that the quantity of the data that we have also have good quality in it, by ensuring that all that we do, we take our quantity and then we qualify it. So in mining terms, we take the data that we have, and then we check our calibrations if they are still in acceptable range. Mostly we will say about, this is depending on what we are measuring. On some instances, we accept 0.5 variancy. In some instances, we accept up to 5% variancy. This is depending on the amount of the data that it gives. So let's say now we are measuring in tons. Obviously, our tolerance will be a bit higher than something that we're measuring in milliamps. So you see, now you do have data, you've collected your data, but then what is it that you need to do? Qualify your data, but ensuring that your quantitative data, you put it through a qualitative system, which in this case you use your accuracy and precision. You see, that's why they come into play. Those two terms, being accurate and being precise, because we need to ensure that we do not kill people. And what we do also, we do calibrations, and we ensure that we put redundant sensor where possible, to ensure that once we have a discrepancy between the two sensors, we must investigate before we use that data. We must investigate. So now we have had our quantity, which now we must investigate to make it to be quality. So yes, some people, they may say quantity, it's better than quality. That will only work if we are looking at a South African rand versus a South African rand. That the more you have more rands with you compared to me that have less rands, then we can say, no, so and so is richer than so and so, simply because of we are measuring them on the same scale of rands. But then now I go to the US or to the UK, and then you come in and you tell me that you are richer than me because you have 1.2 million and then 1.2 million rands, and me, I'm having 900,000 US dollars. You see, by looking at the numerical values, yes, one can say, yeah, no, indeed, the 1.2 million rands is richer than the 900,000 US dollars. But then now, the moment you then put your conversions to it, then you realize that in actual fact, the 900 is richer than the 1.2. So that is where our data comes in, that we have the quantity that we have, but then we need to qualify it, the quality of it, so that we can make well-informed decisions. So another challenge that we have is that our sensors, they drift. You know, over time, whether it's through welding or it's through gluing and all that, they shift from time to time. And unfortunately, this comes to the strength of material. The material that we weld it on, it gets fatigued, it starts to deform, and you know, we have a so-called high precision system, which is a GPS-based system. So now, with that one, the moment a GPS antenna shifts a little bit, we need to come and do survey to ensure that the data that we'll be having will be quality over quantity, you know, because yeah, we can see an antenna is receiving so many GPS what you call positions from our satellites. But then now, if we did not do proper survey on it to ensure that we tell our system that, you know, this is how the machine is positioned based on the GPS coordinates that we have on the machine before starting to move around, you know. So with sensor drifting, there's a gradual deviation from true values over time, and unfortunately, that's reality. And then this is caused by wear, corrosion, or environmental stress. And this now comes to, we need to ensure that we regularly calibrate and validate our instruments or our sensors, so that our qualitative research will be able to address these errors with calibration and redundancy. So that is why I'm saying that with mining or with engineering, qualitative research is not just academic, but it's what we live by. It's if maybe I was in the police force, I would say it's an oath that we take, that in all that we do, will ensure that we do quantitative research that will then qualify the data to become qualitative data. So the two work hand in hand, but then now the quantitative is the main player in this in this manner, because it does not help that you have your instruments calibrated every week, but then there's no data that you're getting from it. What's the use? Waste of money or waste of beautiful resources, you know. And then now you just maybe you just have one or two data that, and now to qualify it, I feel it's small. So we need as much as quantitative data so that we qualify to become our qualitative data. So that's what we do. So, you know, again, with the data that we collect, we have two types of data. We have our active and our passive. So in mining, we rely on these two approaches, which is our active and passive. So active monitoring involves a technician manually collecting samples. For example, you have a technician going to do dust readings or water sampling. So these ones, it's by so doing, we have data that is highly accurate, but it's time consuming, you know. And then now, because of that, we then say, okay, you know what, our active data, as much as it's accurate but time consuming, we may not be able to collect enough data for us to be able to make a decision. So then we say, let us introduce passive monitoring. You see, so passive monitoring will then use sensors to continually collect data from our instruments. So now, you know, with that said, we do have our pros and cons, you know, with active data collection and passive data collection. So, you know, with active data collection, where our technician goes manually and sample dust or water or the benefit of it is that it got high accuracy, you know, and we have targeted insights. But then the problem is it's labor intensive, and then the frequency is limited. So if we are to visit all these machines, you find that maybe once a month, that's when we'll be able to go collect data. But then now, if we then go to passive, where we have automated sensors that will continuously collect data, then the good thing is we'll have real data, and then real-time data, and then we'll have a broad coverage, you know. But then the issue comes that this one, it requires calibration, because if we don't do our calibrations as needed, we may miss our anomalies, you know. So in engineering, so the way we collect data is that we combine both approaches so that we are able to balance the cost, the coverage, and reliability. You know, the cost, which is if we need more data to be collected, and then now we use the active one, it means we need to hire more people, you see. But then now, if we say, okay, we go to passive, we just buy instruments, and then we install them, then we monitor them, we ensure that they are calibrated as often as they should, and then we minimize the cost, and then what do? We then increase the coverage, and we improve our reliability. That's what we need in engineering. That's why we combine active and passive data collection. And then these two, they form part of what? Quantitative data research. You see, because now we need as much quantity as we can. That's why now the active one, it limits us because our technician can only go there maybe once a month. So with that, we have less quantity on our data. And then for us to be able to make proper decisions, we need high quantity on our data so that we can then make quality decisions from our data. You see? So, you know, with that said, colleagues, with reactive versus proactive approaches, you know, there's with mining, traditionally most mining operations, they were mostly working on a reactive approach. So which means that you fix something after it broke. And then that leads to costly downtimes and sometimes even poses safety issues. But with quantitative data, now when we move to qualitative data, which the like of your vibration readings and your temperature trends or pressure anomalies, we are able to predict equipment, on when maybe they can fail or at what interval does a certain component fails. You see, so for example, if maybe we have a sensor that shows a rising vibration on the crusher, we can then schedule maintenance before that crusher actually goes into a breakdown. You see, and then now by so doing, we use quantitative data that we qualify it through our calibration certificates, and we make it to be a quality data so that we are able to be proactive. We move then now from our reactive approach to proactive approach. You see, and by so doing, colleagues, this ensures that quantitative research in engineering becomes our most powerful tool. You see, that's why I said a research in engineering, it is what we live by on a daily basis. So with reactive maintenance, you only act upon equipment failure, and then this one increase unplanned downtimes, and then now unplanned downtimes, it means higher repair costs. You see, and imagine if now you need to fix a conveyor belt after it broke, but then now if you have your quantitative data that you qualify to be qualitative, you can then predict that, this one may break at this certain point, and then now by so estimating, and then you move to being proactive. You see, so being proactive, this one is predictive actions based on sensor data, and then this we are able to prevent failures before they occur. And for example, you can replace a drill bit when vibration exceeds a certain threshold. So we can then tell our data analysis from our sensors to say that, the vibration, because yes, the vibration will be there, but we need to give it a certain threshold, that if it exceeds this threshold, then start checking how often it is. Now you start taking your quantitative data, and then now you qualify it to be a quality data that will then say, okay, we need to replace this, because if we don't, we're going to have a breakdown. So we prevent breakdowns. You see, so as I've said, that we will with the traditional way of mining, you just fix something after it broke. You see, but then now we move into being proactive. That is why we need data. Data make us to be proactive. Yes, Dr. Korombi?
You making very good examples, man. And I just feel that I will forget some of them. I don't know if it is good time for us to pause and we can ask or make some contributions.
Most definitely, Doc. Most definitely.
Yes, I've got this one. This reactive and proactive maintenance.
Yes.
Load shading sometimes is Josienso will tell you that when Medupi fails, why does Josienso not know that Medupi will fail today? Is it that he does not have proactive maintenance strategy? Is he only depending on reactive? Because he should know that now the turbine or any other generating technology is if we have got a strategy to know in advance, if our sensors are working in the way that you're presenting here, we should know that, no, man, in this type of technology will only work for 60 hours. And if Medupi has been operating for 49 or 59 hours, then it means in an hour there's going to be a breakdown. And we will also put a sensor there that will tell us, no, although we say it will only operate for 60 hours, it has got an allowance of maybe 5 hours beyond. Then we should know, man, when it approaches 50 or 60, we should stop it and change or service it, and not be reactive that, oh, we've got 3 megawatts that are down because this was unplanned. We want a planned downtime so that we don't lose a lot and we don't lose business, we don't stay in darkness as the country. Do you have any insight on that or a comment on it?
Yeah, I have a comment, Doc, because insight, I don't want to lie. So let me just give my comment or my analysis from afar. So what I believe is happening, there's 2 possibilities. It's either yes, it is a system use failure, or it's ignorance. Because you can our sensors, they can give us data, but we can choose to ignore it. Or maybe they give us data, but then because we do not calibrate our systems at a given interval, it then gives us wrong readings, and then it makes us to then make decisions that are wrongly informed. You see, so it's I believe that majority of engineering places now, they want to be on proactive maintenance, but then unfortunately we still have the likes of your Medupi. I'm sorry to colleagues that are aligned or associated with Medupi. There's nothing, no credit taken, but this is just my feeling that they need to start using their data correctly. That is why, Doc, I say that you can have your quantitative data. You still need to qualify to become quality data so that you can make well-informed decisions. Because it is possible they are getting data, but then now they don't qualify to become proper quality data.
Thank you very much. I'm grateful. I'm a qualitative person, but you are educating me. I'm becoming quantitative this minute. I'm telling you, I'm becoming quantitative.
Yeah. So Doc, truly speaking, different environments, they call for different methods or different approaches. So hence I say with engineering, truth be told, engineering needs to be driven by quantitative data, which we then qualify it through our calibration certificates, through our sensor redundancy, so that we make it to be qualitative. You see, because it does not help that we just have one set of data that is of quality. You see, we need to be monitoring maybe every 30 seconds or every minute. We need to get readings, or every hour we need to get readings, or every whatever interval that we have, so that we take as much data as we can. And then now we then go to our hypothesis and then check, okay, does this and this really correlate? If not, then go back to re-strategize. Because with engineers, we need to always be in thinking ahead. You see, which we'll cover somewhere in slides 40 somewhere there, that we think ahead. What still need to come, or what's coming, that will better our lives.
Let me comment further. I used to work in the Department of Water and Environment, Department of Water and Sanitation. We used to conduct surface water monitoring. I led the scientific group. I'm not a hard scientist, but I led a scientific group. Then we had this manual monitoring strategy, the active one. I had a group of officials who would go on a monthly basis to go and collect water samples that we took to the laboratory. So that is analyzed to determine the quality of water that we had. That was done monthly. It was labor intensive, I tell you. But at the same time, the department managed to introduce a technology, a real monitoring technology, where we installed probes on strategic positions of our water resources. Those would give you readings almost every time. If there was something that invaded water and it was a substance that is regarded as a pollutant, whether it is chemical or whether it is micro, whatever, the probe at that very station would quickly raise the bar that, oh, here, there's a lot of chemicals. Acid water is coming in here. But when it has passed, then it subsides. It means from minute to minute is going up and down, or it's indicating the amount of chemicals or the acidity that is there in the water from time to time. Then we could, at the end of the month, take this. Then I think we did what we compared with the data that was collected manually to actually, I don't know whether we were doing quality check to see whether the probes were lying or whatever, because the probes will report almost every legal incident. But where we collected manually, we would collect all over different points, but then work on the average to find out the real status of water quality. Then the two, if we compare the two, maybe you could find out. And the other thing is what you talk about calibration. We used to have these instruments calibrated from time to time so that they don't tell us lies. If they are dirty or if it is very hot or whatever, in the way that you were describing, they don't give you accurate data. I don't know whether I have to be precise or whatever. They were not giving you correct data. They were telling a lie. If they are dirty, they will tell you wrong data. But if they are cleaned because they've been calibrated, then they are accurate. They tell you the exact status of the quality of water. So that is what I experienced. And so now it just reminded me that I was actually understanding this quantitative thing, although I'm not a quantitative person. Now, when you explain it here, you were just teaching me, you were reminding me that I'm also an engineer in the making and a quantitative researcher. Then I started to enjoy your session, Yeah.
No, thank you, Doc. Thank you.
Actually,
yeah, the examples that you have used, you are right. So with your dirty what you call your dirty sensor, you then have what is precise data. It will give you values that are almost close to one another, but they're not giving you the accurate readings.
Yes, they are lying because they're dirty. They're not clean.
Yes. So then you go to do quality check. The reason now, as a person, you go and do those samplings is to do quality check, and then now you take your quality checks versus the what you are getting from the sensor, and then you realize no, the sensor is precise but not accurate.
Yes.
And then you go there, you find out it's dirty, and then you clean it. After cleaning it, and then you find out, oh, now the data is precise and accurate based on the readings that we have done as a person.
You've mentioned something very significant, and it's also what applies to me as well. You've mentioned, when you are somehow teaching, that's where you get to learn. And this is how I also learn, even though I've noticed some classes. I remember I got an inbox the other day. Somebody said, what is it that you do, Vele Vele? You are everywhere. Monday's class, you are there. Tuesday's class, and you are talkative, blah, 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 blah. Anyway, this is how I learn. So I'm glad I've got a twin, with the same sentiments. Going into your lecture today, the other thing I would love to tackle this. This is what we call peer-led facilitation. So all of us here, we are peers and we are learning from each other. So I'm just hoping, besides Dr. Korombi and a few other lecturers, they will give us, a platform, because some of us, this is how we learn and retain and excel. So, Mr. Atekani, in terms of your lecture today, very, very impactful, very insightful. It actually reminds me of what the mixed methods that I did the other day. I think 2 weeks ago. And I think if I have to, share my 2 cents worth, data is very important in all walks of life. And although, some of us, we might shy away from quantitative and look at qualitative data, which is perceived to be slightly more, doable. But, you mentioned very important things, such as accuracy and precision. And I remember when I did the lecture, I made an example with a thermometer. And I think the bottom line for me is that if data is not accurate or precise, it's not going to be reliable. So remember that when we look at ethical considerations, there are certain things that we need to tick off, like reliability and so forth. So then we know that definitely it's not going to be reliable, and the trustworthiness. And if we have to repeat and replicate, we might find ourselves with a accuracy that is totally disjointed severely. And then you also mentioned something very significant, which is the variance that sometimes you in engineering you might find, which I'm thinking on my side is the margin of error. So the smaller or the narrower the variance, ideally the much better. But overall, is that my takeaway from your a lecture today is that data, especially even quantitative data, it's very important, and it has a ripple effect in terms of financial, health, economic, ecological, mining and everything, because any slight deviation from precision or accuracy, there might be consequences related to that. So this, I'm speaking most importantly, putting on my nurse's cap on. So yeah, let me pack it there. But well done. I thoroughly enjoyed, and I do apologize for joining late. I had a supervision, but so far, I loved your lecture. Very interesting, and it really rekokotela the nail harder to say data is very important. You have to comb it with a fine tooth comb. Thank you.
I want us to, there is a concept that we always argue here. Look, we always say that quantitative data, quantitative research emphasizes objectivity, and it recommends, the principles are, it recommends less interference of the researcher with the data and the research process. And I want your genuine comment what this implies in terms of your experience, because here you always emphasize proactive maintenance. You always talk about censoring, and you always talk about calibration, and you always talk about ensuring quality, managing quality. And all these aspects are human driven. But we're talking about quantitative data and quantitative research here. And are these people saying it in context when they say we ensure objectivity, or we must then put the process and then stay away from it? Or we just saying no human interference? Because I think they should have written their statements much better, that human interference is needed at the beginning, and When you monitor and you find an abnormality in the system, then you interfere again, calibrating or making sure that GPS, the instrument did not move, is actually on the correct locality so that data can be collected correctly. What can you say about this statement? Because I'm worried about quantitative authors.
Yes, Doc, what I have realized without any academic backups is that as much as you can have your quantitative data, you need to have a certain way to validate it. You need to have a way to make it quality so that you can make an informed decision. Because now, that's now the accuracy and the precision come into play. Because now, let's say now you have precise data. You can then say, if you don't qualify it, you can then say, you know what, this and that, it is not working according to the way it was supposed to work based on your precise data, right? But then now we need data that is precise and accurate on our quantitative collection of data.
Yes.
So unfortunately, I believe that is why they say learning never stops. Maybe after this session, yourself, myself, or whoever can then go like, aha, then they go write something about quantitative data and how they can link it to be that in some certain instances, quantitative alone is not enough.
Yeah.
You see, you still need to have qualitative from your quantitative so that you make well-informed decisions, because there are areas whereby errors will cost someone else's life.
Yes. And you need human interference.
You need human interference.
Validation and corrective measures is human driven.
Yes, Doc. We need that person that will go take samples every now and then to go on the timestamp to say, I've taken my sample on the 26th at 10 o'clock. You go to your quantitative data from your instrument. You go look at that particular time. You check, is there any discrepancy between the two? If yes, is it on a range or a margin that is acceptable? If so, somehow you are able to qualify your data from the quantity that we have got to say, this data, I can qualify it. I move it now from being it just a quantitative data to a quality data because I have done my quality check.
Beautiful, beautiful.
Yes.
And Stanford, I also want to talk about the qualitative researchers. They think that they don't deal with numbers, but they do. Because they always want to interview X number of people. And
so that
they
say, can check the responses.
Yes, and they say, no, we don't care how many people we interview, as long as there is data saturation. What does it mean? No more interesting themes or interesting aspects are emerging, but you already have themes. Themes are numbered. You've got 4 themes or 3 themes, or you've got 3 codes or 4 codes. Those are numbers. Every study has got the qualitative aspect and the quantitative aspect. The frequency of time when a certain statement is made, a qualitative statement would be repeated 3 times or would be repeated by 4 respondents. That is quantitative measure. So people must not. I think these statements are said in a specific context that we would, when we analyze, mainly depend on the quality, but on the other side, we do, when we analyze, will mainly depend on the quantity. But that quantity or quality is supported by quantity and vice versa.
Yes,
So,
Doc, yes.
What do we do? Everything is mixed methods research. There's no way. Everything is mixed methods research.
It's just that in most cases, Doc, there is one that is much superior than the other. I'll give you an example on the research that I'm doing academic-wise. I'm doing a research in cybersecurity.
Yes.
You know, there my main focus is on quality, because then what happens is I have insights that when someone speaks, I'm able to pick up the truth on the statement that they are saying. You know, so yes, me I am a bit this and that. So on the engineering approach, because you know your suggestion was it must be in engineering approach. With engineering approach, I knew for sure we need data, quantity.
Yes.
So that's why I came with that. So if you said qualitative, I would have then moved from now being so much in engineering to cybersecurity, the one that focus on quality.
And that is your actual academic study.
Yes, cybersecurity is correct.
Did you start collecting data on that one, Stanford?
Doc, I did, but I'm still in the process of having to analyze my data. So you know, so the role of quantitative data in engineering, especially in mining, it enables us to detect where stress and anomalies earlier before they can actually happen. You know, and then now that's it, and then moves the operation from being reactive to proactive, because now they have data to work on. You know, because without data you cannot be proactive. You need data to be proactive. So quantitative data helps us to move from being reactive to be proactive, and then by so doing, we then improve on safety, on efficiency, and cost control. So that's where we are. So you know, in mining, we have what we call KPIs, or key performance indicators. So these are essential to track how well mining operations are performing. You know, you then check the utilizations. It tells us how efficient we're using our equipment, and then downtimes it will show us where we're losing productivity, you know, and efficiency. Energy efficiency helps us to manage costs and environmental impact, you know. And then, and the biggest thing in mining is that safety, it is non-negotiable. So quantitative data, it helps us to track incidents, to protect our workforce and meet the standards that the DMR have set for us, you know. And then and recovery rate is direct measure of how much value we are extracting from maybe the ore that we process, you know. So now together with different metrics, it gives us clear data-driven view of the operation. You know, so qualitative research helps us to not just only to measure these KPIs, but also to improve them through predictive insights and continually monitoring our systems. You see, so I did touch up a bit on the utilization. You know, so now moving to our downtime, you know, with this one, we have KPIs that are data driven to tell us, or to give us our what you call our delays, our outages, you know, and all that, so that we can drive our downtime to be lower. Because if we have a lower the downtime, it means we have a higher productivity, you know. And then again, now from there, I've touched also on energy efficiency, you know. So because we need to ensure that we minimize the energy that we consume per ton. You see, by minimizing that, and then it means that we optimize the cost and the impact on the environment. Because remember, energy comes from environment. and it have an environmental impact. You see, and then now with safety, quantitative data, it helps us to then quantify the incidents that we have had, so that we can then know our what you call our the well-being of our workforce, and then we can ensure that we comply to what the DMRE have said, Department of Mineral Resources, and then we also know that how many, even though we're not proud, but we need to know how many people we've injured, you know, and then how many people did we kill, though we're not proud, but then it happens. That's why we need quantitative data that is of quality to make informed decision. You see, then from there, we take all these and then go to our recovery rate, because from all that, from utilization, our downtime, and our energy efficiency, and our safety, we need to recover, because in everything that we do, we always want to achieve the best that we were yesterday. Because remember, there's a saying that today's best become tomorrow's standards. So we need to ensure that we beat what is of standard today, so that tomorrow we do it better, whether in utilization, in time, in efficiency, in safety. We need to do that. And we cannot do that without data, quantitative data that will qualify to become qualitative. I know today our main focus is quantitative data in engineering, but I'm going to tell you, in engineering, in most cases, quantitative data alone will not give you the result that you need. But then it takes a bigger chunk of what we have on the plate, you know, because for us to be able to qualify it, we need as much data as possible. That is why we have all these sensors on the field. And then now we'll have Dr. Kurumbi going and taking the samples every now and then to ensure that we then qualify this data for it to not just precise, but being precise and accurate. You see, because now when we have that, we have a high recovery, which will lead a better profitability. So where do we get our data in mining? I'm gonna be a bit fast, colleagues will forgive me, because we're left with 30 minutes. So I'll try to do catch up within the next 30 minutes, so that I share what I have with you. So if somewhere I move a bit fast, please do stop me, and let's discuss about it. I believe that colleagues will forgive us if we happen to go overboard on time. So with mining, we get our data from IoT sensors. With IoT sensors, they give us real-time monitoring of vibration, temperature, pressure, moisture, or most of the things that you can think of, we're able to measure. And then by measuring, it gives us the quantitative data that we need. You know, so these sensors, they're installed on equipment, conveyor belts, or stockpiles, and underground systems. You know, because sometimes maybe you may want to measure your moist on your stockpile, or you want to measure your vibration on your conveyor belt, you want to measure your temperature on your underground, you know. So you have these IoT sensors that they get integrated to what we call a SCADA system. You know, so SCADA system simply means supervisory control and data acquisition. So this acquires the data from our IoT sensors. These sensors, they are the ones that they are there in the field, in those dangerous places that we don't want our technicians to be in. You see, so with the SCADA system, it's centralized to a control of machineries, flow rates, and processes variables. Dr. Kurumbi did mention that they had probes that they've installed in different aspects or in different points in the plant. So usually those probes, they then go to a SCADA system. A SCADA system takes that data in real time it can be a delay of like 5 seconds, but we still classify it as real time based on the what you call on the discriminations that it's allowable. So that data, we then take it, we put it on the SCADA system. So the SCADA system is able to give you the live view of data. But then be very careful, not just to rely on the SCADA system. Because remember, this one is taking data from where? From your sensors. The sensors that needs to be qualified by checking your vibrations, whether they are dirty, whether there's the taking because of the temperature and dust and all that. You see, so as much as we may have these systems that give us a time-stamped and structured data for analysis, we still need to go and verify it to say, okay, at this certain timestamp, this is what I, as a person, based on my qualitative data collection, I found. Then I go to my quantitative data to check on a timestamp to say, oh, at this particular time, this is the reading that I got from the exercise that I did, and this is what the system gave me. And you check accuracy and precision on that. You see, so, and also we get our data from laboratory analysis, you know. So this you from your ore grade, you take your ore, go to the lab, or your water quality or dust concentration to check on the dust, what is it, what chemicals are available on the dust. So all these three, you can take them to the lab, and then you do your tests. You see, then after doing your test, you go. So you see now, when you do your tests, you are doing actually what I call it qualitative data collection. You see, the test from the real thing, and then you take your qualitative data collection, you then compare it with the quantitative data collection, which is the data from your sensors. And then after doing that, you will come up with high accuracy data that you will use to calibrate, if need be, and validate the data that you have collected. You see, so, and then now also, when it comes to a machine operation, we also rely on manual entries from technicians' inspections, start of shift inspections by the operator and the supervisor, you know, and this includes observations, anomalies, and conditional notes. So now with this, you know, this one now it's your active data collection, because you need a person to manually capture something. You see, so now maybe on a start of shift, our tech or our operator or supervisor captured something, and then we take that information, and then we compare it with our passive data. And then when we do that, and if we do notice that there is indeed something in a similar between the two, we then react on it. You see, now, because a human being, when they go there and do those inspections, they're giving us a qualitative, qualitative data. But then our instruments, they give us quantitative data. We take the two and we make a comparison to make sure that they are accurate and precise, so that we can make a well-informed decision. You see? And then again, with safety reports, we need to, there is no engineering without safety reports. In most of the times, if you enter an engineering place, you will see, safety or incidents free, whatever. It's the biggest thing that you'll see, because we believe in ensuring that whoever that comes to the environment need to go home safely. So now we need to ensure that we do incident tracking, near miss, and we need to make sure that we do compliance audits, so that when the principal comes, the principal of inspectors come, we're able to give them the audits and all the incidences that we have captured. You see, and then now this forms part of the risk assessments that we do, and to ensure that we report regularly in a manner that it's recommended by the DMRE. So now, with quantitative research in action, we have different data analysis techniques. We have descriptive statistics, whereby we summarize the sensor data. So now we'll have our mean values, our median values, and our standard deviation. So now, for example, maybe on a crusher, you want to you have your average vibration levels across all crushers. So now here you will have set a certain threshold that, our crusher must not vibrate above this threshold, this number. If it does that, and then on a repeated what you call sequence, it then poses the need to go verify the quantitative data that we've got, so that we make well-informed decision. And then now again, there's also the regression models. This one reveals the relationship between the variables. As I've said, that there may be a variation, a little bit of variation. For example, you want to predict if the drill bit were from the RPM and rock hardness. So RPM is rotations per minute. So that you will understand whether for you to protect your drill bit not to work quickly on the hard surface, maybe you need to reduce or increase your rotations per minute. All this, it comes from your quantitative data that you have collected. And then now, after you have collected your quantitative data, and then you qualify it to become qualitative, so that you can make a well-informed decision. Because now you don't want a situation whereby you then make a decision that is wrongly misled by the data that you've collected, and you find that because it is precise, not accurate, and then you feel that it is acceptable, and then you make a decision based on that. And then when you make a decision based on that, you are you are setting yourself for a failure, because that data is not accurate, but it's precise. So in engineering, we do not need accurate or precise. We need it to be accurate and precise. Those two must go together, always. So and then now, so there's also time series forecasting. This one tracks the trends and predict future values, and this is it's able to make us to be well informed when we need to do our predictive maintenance. And then we have our anomaly detection. This one, it will reflect, it flags outliers and early warning signs, and still this one also adds to the what you call the KPIs that we use to then estimate a piece of equipment failure, because we need data to estimate a certain lifespan of an equipment. And that data must be accurate and precise. I'm going to be preaching these two every now and then, because it is what we need. And truly speaking, in every discipline, we need data that is accurate and precise. Because once we only have one of the two, we may be going for a failure. And then so now, with that said, we do have failures, in quantitative data analysis. So now we then say, okay, with the facts that we need to have what you call a way to prevent this catastrophic situation happening. So we then let me maybe give you a lifetime, a real life scenario. So I won't be really talking through the slides, but what I'm going to be saying will relate to the slides. So that, and this will show you the power of quantitative research in mining operations. you know. So maybe let's look at a crusher, you know, which is a critical piece of equipment in mining. So back then, or historically, it failed without a warning, you know, which caused so much downtime and production delays, simply because we did not have sensors connected or mounted on it to give us data to monitor it. You see, so to address this, we installed sensors to monitor vibration levels in real time. You see, and then over a 90-day period, maybe, or whatever a time frame that you put, but mostly it's a 90-day period, which is 3 months. You know, we collect high frequency data. So now, using descriptive statistics, we can then establish a baseline operating range. You see, and then now, after that, we then move to regression modeling. This one, it will help us to link the rising vibration levels to a bearing wear, because mostly in a crusher, we use something called a bearing, you see, which there's wear and tear, because there's grinding of what you call, there's grinding of metals there. So wear and tear is possible. And then now, so with a time series forecasting projected, you may find that maybe there's a spike in maybe in 12 weeks time or 10 weeks time, you know, and then now with that spike, you realize that there is an anomaly detection. Maybe there's a certain a jump on your vibration data to say that, you know what, now we are vibrating on about maybe 4.6 gram instead of about 3.5, which is the threshold that we have set. You see, so now when that happens, then the alert is triggered, you know, to do a proactive intervention. You see, and then now we then get to replace the bearings before they occur, and as a result, you find out maybe you avoid about, based on rough data from head, about maybe 18 hours of downtime. And then if you then now need to put it on money value, maybe about 240,000, you know, in repair and loss of production costs. You see, and then now if you check, this is not just a technical win, but it was a strategic shift. You know, quantitative analysis, it turned raw data into actionable insight. It prevented failures, protected operations, and demonstrated how structured data can drive smarter and safer decisions. You see, and this is the kind of impact we aim for when we integrate instrumentation with analytic data. You see, and then this data comes from where? From our quantitative data collection. You see, which is not just about collecting data, but it's about engineering foresight. Because without any foresight from the data that we need in engineering, there's nothing that we can say we are succeeding on. You see, so this in the bit of the explanation that I've said there, I did cover a majority of it.
You are continuing to baptize us into quantitative research. I spoke about the predictability of the failure of the power stations and the turbines. But here there is something that specifically relates to the mining operations. We always hear that people are trapped in mines, and this is mainly because of the collapse of the slope. Now, your technology, your sensoring technology can determine if the slope is about to collapse. And I think it should be able to warn people that, no, this would collapse in 30 hours or in 2 minutes or whatever. Please escape, run away. We always hear that people are trapped, but we never have heard that Medupi power station or a specific mine has actually rescued people by warning them prior to the collapse of a shaft. We don't hear that. Why does engineering news not report those positive things? Is it that they are unable to detect it in advance and they only are reactive after the collapse?
Doc, to give you a straightforward answer, we are able to detect that. And then the reason you hear of those is that bad news is selling news. If you do, yes, truly speaking, we have had instances where people were evacuated and all that, but because nothing bad happened, that news does not sell. Bad news is selling news. Unfortunately, that's the reality of the life that we're living in. No matter how good you do, someone may overlook it, but do bad. We saw Dr. Kurumi being drunk in such a way that he cannot even walk.
Yes.
But the good that you have done, no one says anything about it. But do something bad, we will talk.
Yeah. Quite interesting.
So unfortunately, that's the world that we live in. Because now, Dr. Korombi, if I put that in research, they end up using a qualitative without looking at quantitative. They don't quantify the good. They only focus on the quality of the bed. To say this bed have a what you call it, have a backup on it that indeed people died. So they lean more on qualitative research. But then now, if you were to look on the failures and the successes, you may find out that the successes are much higher than the failures, in such a way that if we were to then scrutinize between the two and make a comparison, the bad news was not even supposed to be said if we even said 5% of the good.
Yes.
Beautiful. I believe that our journalists, if the journalist colleagues, they may wrong me if I feel I'm right, that in most of the time they go with qualitative. They go with what they see, what is indeed have a proof that it happened. You see, so that is where research comes in. As I've said, different disciplines, they do or they prefer different research methods. You see, I believe our colleagues on the side of journalism, they weigh more on qualitative data and quantitative. But in our case, we weigh more on quantitative than quantitative. So yes, that's how it is. So now, with this, I'm just gonna do a quick runabout. So with qualitative research, as much as it gives us structure and clarity, it's not perfect, should be told. It's not perfect. In mining, to be specific, we have dust, we have heat that can interfere with sensors. And over time, even the best instruments drift and it needs calibration. So with thousands of data points streaming in every second, it's easy to get overwhelmed. And there's also the risk of missing context, and the numbers tells us what happened, but not always why. You see, numbers, they can say that there was a vibration, but why? They don't tell us. That's why we need the operator logs, you see, and the quantitative insights, because they are important in this regard. You see, so you see, now we then mix the two. From being it quantitative, we need the qualitative insights from the operator logs to qualify the data that we have. Because numbers, they can tell us what happened, but not why. You see? And of course, we must be vigilant about ethics, especially when the data influences safety decisions, because that is where the biggest part plays. So what I can say is integrating data across disciplines is a challenge, truth be told, whether in engineering, in health science, in economists, everywhere. speak of different data languages and all that. So if we can be able to bring those gaps, truly it is going to be of great results. So all these are about the challenges that we come across, which are just summarized not long back. You see, so now to overcome these challenges, we need to do regular calibrations. We need to ensure that we come up with hybrid data models whereby we combine data sensor and operator logs to ensure that we then take the quantitative data and we make it to be of quality. You see, this one will improve our context and reduce our blind spots. You see, and then also we need to do, with sensors, we have a challenge of something called noise, and so we need to do noise filtering and signal processing. So noise can be temperature, it classified as noise, and anything that have an impact on our data, we classify it as noise. It's not about the noise that you hear when someone is shouting or there's a group of people talking and all that. In engineering, when we say noise, we say we're referring to anything that have impact on our data quality. You see, so now we to ensure that we overcome these limitations, we can then rely on noise filtering and signal processing. And this is essential for high frequency sensor streams. And then also we need to compensate for the environmental changes. We need to make sure that we adjust our sensors for dust, for heat, vibration interferences. If maybe what we want from those sensors have nothing to do with vibration, because vibration can be a noise to our data. Remember, in engineering, when we say noise, we are referring to anything that can impact the quality of our data. You see, that's what we call noise. So let's not be lost there. And then again, we can then have ethical and compliance frameworks. In all that we do, data and whichever mode or method of data research that we do, we need to ensure that we are ethical and compliant about it. You see, so that we align with the standards that have been set, and we can ensure integrity of what we've done. We say you must always do the right thing the right way all the time, even when no one is watching. So never manipulate your data, because once you manipulate your data, you are then not bringing a true reflection of what the data brings. You see? And then now we also integrate across different tools. We have ontologies, we have dashboards, we have semantic models to unify data. So the moment you unify your data, your passive and active, you are able to come up with a good collaboration in your data. And this works in whether in engineering environment or whichever aspect that you may think of. So I did speak of for the future, what the future holds for us when it comes to data collection. So in the future, I believe there will be some AI-driven predictive analysis. There's machine learning. Because with machine learning, it anticipates equipment failure, it optimizes energy use and focus on ore quality, for example. So with machine learning, it gives us real-time decision making with minimal human intervention. Some of us may lose our job because of this, but I did not say it. So, and then there's also semantic data integration. This is for the future. This is where I feel the future is going. So and ontology is the backbone of every system. Ontologies, they are there in finance, environment, in health, in engineering, everywhere there's an ontology, because everything that happens need to have a nerve system. So this one, it enhances interoperability between engineering, safety, and environmental systems. And then now there's something we call edge computing for sensor networks. You see, so this one, it will give us real data processing at a source. So now this one, it will reduce latency and improves responsiveness in remote mining environments. So meaning that in most of the times, we're not going to be in need of people to go do data verification, because with AI, it's like a child. The more you feed it with information, the more it learns, the more it is able to detect variances between data. So AI can then give us a recommendation of flags to say that, what, check your calibration data, check your positioning, because it seems like it could have shifted maybe a centimeter or a millimeter or whatever the case may be, based on the threshold that is being given, And then now we have a blockchain for data integrity, So this one is immutable records of data, safety logs, and compliance records. And this will build trust in audits, certifications, and cross-organizational collaboration. Because in all that we do as an organization, we need to collaborate. You see, and then now there's something called digital twins and simulation models. With digital twins, you can basically you can have two sensors in one place. You calibrate them to ensure that they give you more or less the same data based on the position that you have placed them. So with these two, they must give you precise and accurate data that will support learning, training, and risk mitigation. You see, and then now we need to also come with matrices that will be integrated. So quantitative tracking of emissions, maybe, and water usage. This one will align with mining operations, with environment, social, and governance goals. You see, so now in closing, my takeaway from this is that I hope we have understood how structured data drives smarter decisions. In instrumentations, we bridge theory and we bring those bridges between theory and practice. So what I want to leave you with tonight is that quantitative research is more than just measurements. It's a mindset, one that values clarity, structure, impact, and this is whether we are in preventing equipment failure, or improving safety, or modeling environmental risks. The tools we have explored today, they help us to move from reaction to what you call to being proactive, and even though most of my examples they came from mining, the principle applies everywhere, whether in health, in education, economics. Structured data leads to better decisions. Always remember that, So let's keep asking questions, collecting evidence, and with engineering insights. Colleagues, before I go to my closing slide, any questions, any inputs? I tried to cover up the time. Sorry, I'm 4 minutes late. Questions, inputs are more than welcome. Dr. Korombi?
Yes, you did not tell us that this is applied research, but I think it is.
Yes, it is. It is, Doc. It is.
You were presenting real data and real project that you're doing on the ground. It's not only academic. So this is an example of what we refer to as applied research, because this solves existing problems in the mining operation. It's not waiting to solve future problems, and it's not only meant to improve our understanding of the mining operations or the engineering technology, but it's actually solving them now as we speak and as we conduct the research.
And as I think I've said that, with quantitative data research in mining, it's not about academic. It's what we live by on a daily basis. That's what we live by. Actually, in engineering as a whole, quantitative data is what we live by, because without data, we're nothing. Because when we extract data, we extract meaning. My closing line comes from Edwards. He says, without data, you are just a person with an opinion. So ensure that you collect data so that you become a person with effect. Thank you very much. That's all from me.
Pleasure. Thank you very much. Let's clap again for a wonderful presentation. And colleagues, I think I've enjoyed this in the way that it was presented, very well presented. So you still have, Stanford, you don't have time to present the qualitative aspect from an engineering perspective, but you have that presentation.
No, I don't have that presentation, Doc, because remember, I think I saw your message Saturday evening. So I had a very limited time. Luckily, I was on my off day, so I was able to come up with the presentation.
Okay. Okay.
Yeah. So if I move to quantitative to qualitative, it means then now I'll shift a bit from engineering to information technology, because cybersecurity is not so much in engineering but in information technology.
Okay, beautiful, beautiful.
Which I have a problem with doing, but I'm not promising when.
Okay, thank you very much. But if you will have chance to prepare something, please do so. And I'm saying it to you because I see that you can do it. But on the same breath, I'm not saying it to you, Stanford. I'm saying it to everybody here. Those people that still have the opportunity to present, that still have something to share with us, they should not be afraid. They should come on here. I like your presentation because you have got part of data collection and data analysis. And I want colleagues that have gone to the field, that have collected data, colleagues that have analyzed data to share with us how it looks like, so that you sharpen our understanding. We can ask you questions and you can clarify to us. And I see there are people who are approaching me. Don't fear. I'm still going to bring some people here, because on Thursday would bring Kidi here. Kidi Boni would do a presentation. It's on mixed methods, but she has collected data. We'll be seeing her indicating to us how she collected and how she is analyzing, or she's finalizing the research report. But those people, Ererwani, have you not started collecting data? Agricultural and environmental sciences? Ererwani?
Doc, maybe when Ererwani is coming, for me, the reason it was easier for me with the short time that I had to prepare this, it's simply because it's something that I work with on a daily basis. It makes sense to me. You understand? Hence, I kept on emphasizing that it is not about academic work. It's what we do on a daily basis as engineers. We live and we decide by quantitative data that will qualify it through our calibrations and our what you call our active data collections and all that, and also to show that why we collect it, so that we move from being reactive to proactive.
Thank you, Dr. Korombi. I guess this is what we call peer learning in some of our terminology, where we learn from one another, because it would seem that every week someone brings in something new. And may I please take this opportunity to thank our guest presenter, Stanford Khosa, for taking the time to share his applied research and what he has done so far. I'm sure that most of us, or if not all of us, have definitely picked a thing or two. Thank you, Mr. Khosa. I'm sure we will tap into your knowledge again, because opportunities will definitely arise. We still have quite a lot of time to the end of or mid-November for us to keep sharing.